Welcome back, everybody, to the second day of lectures on hypothesis testing. We're still focusing on hypothesis testing for population means. Our last day of lecture will talk about a different population parameter, specifically a population proportion. But today, I want to talk in more detail about these different types of hypothesis tests in terms of directions of extremity. So let's quickly just review our process. Remember, every hypothesis test starts out by writing out the hypotheses. So based on a claim, we're going to write out a null and an alternative hypothesis. And remember, our general goal is for us to reject the null hypothesis or disprove the null hypothesis using sample data. So we're going to get some data, or at least a problem that gives us some sample statistics. And we're going to have to typically compute a sample mean, a sample standard deviation, and a sample size. We're going to take the sample mean, this is what we collected from our actual population, and we want to convert it to a t-score. So this is something we call our test statistic. It's the t-score version of our sample mean, as represented by assuming that the null hypothesis is true. Right, so we have a formula. We've done one or two problems working with this. We'll see a lot more examples of it today. We'll do some more practice. Once we have our t-score, we're going to find the probability of getting t-hat, our test statistic, or something more extreme. We call this probability the p-value for the hypothesis test. Finally, once you know the p-value, we choose from two possible conclusions. If the p-value is below your significance level, and this is something that we set as researchers, much like with confidence intervals, we set our own confidence level. If our p-value is below our significance level, we have evidence to reject H0. And in our analogy to the criminal justice system, having a p-value below the significance level is like proving the sample shows beyond a reasonable doubt that we can reject that H0 value, or that H0 hypothesis, right? If the p-value ends up being above your significance level, there's still reasonable doubt there. So you failed to provide enough evidence to reject H0. The prosecution fails to show that that H0 is guilty or false. All right, so based on the p-value we end up computing and the significance level that we as researchers set, we'll have a clear delineation as to whether we have evidence to reject H0 or we failed to provide enough evidence to reject H0. So remember our little heuristic example. We were looking at Labrador retrievers. I had a colleague who claimed that the mean weight for all Labrador retrievers is 60 pounds or less. We collected a simple random sample of 12 dogs and found a sample mean weight to be 79.3. Converting everything to t-scores using our t-hat formula, we got the sample mean we collected corresponded to a t-distribution value of 4.46, assuming that the null hypothesis is true. Now, the probability of observing a sample mean like that or something more extreme, we ended up changing into a probability of having a t-score that's above that 4.46 value. So a t-score above our test statistic. And this we went into Excel and actually computed. It was a very small p-value. So we ended up rejecting our colleague's claim that the mean weight for labs was less than or equal to 60. So what I want to focus on in this particular lecture, before we do a collection of examples, is this phrase in step 4, using the t-distribution and our test statistic, find the probability of getting a test statistic value like the one we computed, or something more extreme. That's really where I want to focus. How do we determine extremity when we're doing these hypothesis tests? There's 3 different types of tests, and they're all associated to the way that your null and alternative hypotheses look. So if you start by testing a claim that the population mean is greater than or equal to some value, we're going to call this thing a left-tailed test. Now notice that the alternative hypothesis is that the real mu in the population is actually less than the proposed value C. Right? So typically when you're trying to figure out the direction of extremity, you look towards the alternative hypothesis. And that inequality is going to be pointing in the direction that you would consider more extreme than the test statistic value that you actually computed. Okay, so this is the picture that we see for a particular setup for hypothesis testing. When your null hypothesis is mu is greater than or equal to c, the alternative is that mu is less than c, which leads to a picture that looks like this. When we go to actually compute our p-value, it's going to be the area in the left tail, which starts at the computed test statistic t hat. So our p-value is going to already be in cumulative form. So we can jump directly to using t.dist. When we're doing a right-tailed test, these are the past two examples that we did during our last lectures were both right-tailed tests. This is the case where you have a null hypothesis where your population mean is less than or equal to a value. So the alternative hypothesis is that that true population mean is actually greater than c. So the region that supports the alternative hypothesis is farther off to the right. And again, if you kind of look at I'm having trouble highlighting there. If you look at just the alternative hypothesis here, the direction of that inequality points to the right. So that's sort of our hint. We want to look in that rightward direction. Now in this case, when we go to compute our p-value, we want the likelihood that we have a test statistic or something more extreme. Since the direction of extremity is to the right, we're actually going to compute probability that t is greater than or equal to our test statistic. So it's a little bit different. The last type of test to consider is when our null hypothesis just makes a claim of equality. So it's not a less than or equal, it's not a greater than or equal, it's just equal. If we have a null hypothesis where mu is equal to a value c, the alternative hypothesis is that the mean is different from c. Right? That population mean is not equal to c. And there's two ways that this could happen. You could have a true population mean that's greater, or you could have a population mean that's smaller. And for that reason, since there's two ways that you could describe them being unequal, we end up having two tails when we end up drawing our sampling distribution extreme regions. So for the one tail, off to the right, this would correspond to being bigger. We're going to use the absolute value of our test statistic because remember with the t-distribution, if you're out in this right tail, this value has to be positive. And all the absolute value does is it just takes away a negative sign if it happens to be there. So this guarantees that our right tail always starts at a positive value. And we use that same magnitude, but we negate it to be the start of our left tail. So the absolute value is just saying, forget about the sign for a second, put the positive version to the right, put the negative version to the left, and now we can start thinking about what our p-value would be. The p-value ends up being the area in both of these tails. And the shortcut way of computing this is to just look at the left tail. So the probability your t-distribution is less than or equal to this negative absolute value of t hat. Again, this looks scarier than it is. It's just going to be take whatever test statistic value you have and make sure it's a negative version of it. Right. So the area in the left tail is computed by this probability here. And since the t-distribution is symmetric, the area in the right tail is going to be exactly the same. So we can simplify our computation by just computing the left-tailed area and then doubling it. So this is how we're going to approach these different regions of extremity. Once we know the null hypothesis, we'll know the type of test, and that will give us a formula for how we're supposed to compute the p-values. Okay? All right. So here are all three different types of tests. All extreme regions are based on the actual test statistic, your sample mean converted to a t-score. So you'll notice t hat is appearing in all of these different formulas for the test statistic. You'll also notice that the alternative hypothesis gives you sort of the direction of the extremity, right? When the alternative is less than or equal to c, notice that inequality is pointing to the left. So we call this a left-tailed test. And we would want the probability that we get t-score values to the left of our t hat. Similarly, when our alternative hypothesis is that mu is greater than c, that inequality is pointing to the right. So this is a right-tailed test, and that means we want the probability that we're to the right of our test statistic. The two-tailed test is the one that's a little bit trickier. I find it's helpful to just draw the picture. Think about what the left tail would look like, and then double that probability. All right, so let's do a little p-value speed round just to get a sense for how this works. So we're going to cut out sort of the general word problem nature of this stuff. I'm just going to cut directly to the type of test and the test statistic, and we'll see if we can figure out how to compute these p-values. All right, so we have a right-tailed test, and we're computing a test statistic t-hat of 1.93. The sample size is 46. So how would we get the p-value? So a good idea as we're doing these in the speed round, pause the video, make your best guess, and then see if you get the right answer by hitting play. All right, so in this case, the extreme region would be to the right. It's a right-tailed test, so the extreme region is to the right of our test statistic. So to compute our p-value, we would want the area in the right tail of this picture. So since we're not in cumulative form, we're looking to the right of 1.93, not to the left, we have to do the 1 minus trick in computing this p-value. So our final answer would be 1 minus t dot dist, 1.93, 45, remember, is our degrees of freedom, 46 minus 1. And then the last cumulative argument is always true. Next, we consider left-tailed tests. Suppose we have a left-tailed test and we compute a test statistic of negative 2.12. Assume the sample size is 103. How would we compute the p-value? Now, before you pause the video, let me just mention that typically speaking, when you're doing right-tailed tests, your test statistic t-hat will be positive. When you're doing left-tailed tests, the test statistic will be negative. And when you're doing two-tailed tests, it could be either or, which is why we need our absolute value. But anyways, let's pause this video, see if you can compute or think about how to compute your p-value in this case. All right, let's check. So since this is a left-tailed test, the region of extremity would be to the left of our test statistic. So the p-value is going to be the area in that tail. So the area in the left tail, well, this is already in cumulative form. So we're looking at the probability that t is less than or equal to negative 2.12, and we can get this directly using a t.dist command. The last example I want to consider is a two-tailed test. Right? So we have a two-tailed test. We compute a test statistic of 2.37 and assume that the sample size is 57. Now in this case, pause the video and see if you can remember how to compute the p-value for the two-tailed test. Okay, so our test statistic is positive. So in this case, when we draw our picture, remember we're going to shade in two tails. And the start of the left-hand tail, it's just going to be the negative version of the test statistic that we already computed. The p-value itself is the area in both tails. But remember, the way we're going to approach this is by computing the area just in the left tail and then doubling it. The reason we focus on the left tail is because that probability is already cumulative. If we were to focus on the right tail, we'd have to do a 1 minus trick. So it's quicker to say, all right, what's the probability in the left tail? That's already cumulative, t less than or equal to negative 2.37, and then double that. So in Excel, we can just do 2 times t.dist negative 2.37. 56 is our degrees of freedom. And then finally, our cumulative argument is always set to true. So this is how we would work with two-tailed, left-tailed, and right-tailed tests. Now that the speed round is over, I want to go over 3 examples, one of each type, in Excel. When we're working with data, we'll have to do the computations, and we'll have to find our p-values and make our appropriate conclusions. So this is the whole kit and caboodle, the whole process all together, doing different types of tests, working with sample data, and hopefully really solidifying your understanding of hypothesis testing for population means. All right, let's get started.